Welcome to the episode 4 of our series, The Mother Earth. In episode 3, we viewed how the compositional characteristics of the solar system connect its origin to a supernova explosion in our galaxy, the Milky Way. The solar system condensed from a huge nebula that got mixed also with the gaseous clouds of the then existing interstellar material. The event gave birth to a younger star like the Sun and the planetary nebulae that condensed eventually as planets. When did this event occur? That is the question we are addressing in this episode. To fathom the depth of time since the solar system came into existence, a scale was needed that could measure time in millions or billions of years. The decay systems of certain radiogenic isotopes provided that scale. It was necessary also to examine and find the age of the material constituting the meteorites that impacted the surface of the Earth. The meteorites coming from the asteroid belt also formed along with the solar system, dating the oldest meteorites and the oldest rocks on Earth and eventually on the Moon, provided additional evidence that revealed how old was the solar system. In stellar nucleosynthesis, many such nuclides of elements are also produced which have the same Z, that is the number of protons, but differ in number of neutrons, that is N. Naturally, the N by Z ratio in such nuclides differs. Such nuclides are referred to as isotopes of that element. Not all such isotopes are as stable and abundant as that isotope in which the N by Z ratio is unity. Alternatively, we have also learnt that stable nuclides should have even mass numbers or have even Z and N. For example, amongst the three isotopes of oxygen, namely O16, O17 and O18, only O16 is the most stable and hence most abundant. The same is applicable to calcium-40, which is the most stable amongst 6 of its isotopes. Among the three isotopes of silicon, only silicon-28 is the most stable. And we have also learnt that Fe56 is the most stable among its 4 isotopes. These different isotopes of elements are obviously produced by accommodating more number of neutrons as N by Z varies. They have formed almost at the near peak temperature conditions of about 10 to the power 10 degrees centigrade in the stellar cores. Beyond calcium-40, the N by Z ratio increases, and even beyond Fe56, elements with lower abundance are formed during the conditions of the supernova explosion by capturing extra neutrons available till the production of bismuth 209 with atomic number 83, in which the ratio exceeds 1.5. Elements with mass number A greater than 209 disintegrate spontaneously and decay to a more stable nuclide and ultimately achieve the nuclear stability. Samarium-147, with a much lower mass number than that of bismuth, also undergoes spontaneous decay to reach the more stable nuclide neodymium-144 amongst the rare earth elements. This is an exception. This decay process is exothermic, and the decay transitions before reaching the final stable nuclide of an element are always accompanied by emission of alpha, beta, or gamma radiations. The alpha particles are positively charged, while the beta particles are negatively charged, and the gamma rays are electromagnetic waves. That is why this spontaneous decay and formation of a new stable nuclide is referred to as the radioactive decay process. This energy emission is referred to as radioactivity. It always results in either a change in N or in Z, that is the atomic number. You know that whenever there is a change in Z, a new element is produced. In many of these decay systems, helium-4 particles are emitted, which are referred to as alpha particles, with 2 protons and 2 neutrons. For example, when radium-226 decays to radon-222, the alpha particles are emitted. The emission of alpha particles changes the mass number A to A-4 and Z to Z+2, releasing simultaneously quantum energy. The decay of uranium-235 to thorium-231 also emits alpha particles, bringing about the same changes in A and Z. If a proton gets added to the nucleus by conversion of a neutron, it emits charged beta particles, which are electrons. In this process, no change occurs in A, but Z becomes Z+1 and N becomes N-1. When a new element is produced by such emission, it is also imparting a change in the binding energy of the nucleus. This process by which a new element is formed is referred to as neutron capture. The nuclide rubidium-87 decaying to strontium-87 with higher atomic number provides an excellent example of a beta emitter and neutron capturing. Strontium-87 is a stable isotope which does not decay further, and therefore its amount in any sample is taken as a radiogenic product of rubidium-87. The decay of uranium-235 to thorium-231 can also take place by a change in only A as A-4 and with emission of gamma rays. The decay of potassium-40 nuclide provides another unique example. Potassium forms a stable nuclide, potassium-39, and also an unstable radioactive nuclide, potassium-40. 80% or more than 80% of the nuclide potassium-40 decays to calcium-40, accompanied by beta particle emission, and the rest of the potassium 40 decays to argon 40. The decaying of potassium 40 to argon 40 takes place by a process referred to as the electron capturing. In this process, an electron is pulled into the nucleus and is converted into a proton and a neutron. In either case, the number of protons changes, and we know that whenever it happens, a new chemical element is created. Radioactive decay is also not a linear process. It is also an exponential process. It implies that the rates of decay remains constant for a very long time, say millions of years, or for a very short time, infinitesimal time, usually denoted by dt. It also implies that the number of atoms disintegrating per unit time is expressed as minus dn upon dt is proportional to the total number n of radioactive atoms present in the sample. This is stated as the law of radioactive decay. The number of nuclides disintegrated is an exponential function of the time taken to decay. Thus one writes a differential equation, minus dn upon dt is equal to lambda n, denoting that the rate of change of the number of decaying atoms with respect to the time that lapsed. One may also write this equation as dn upon dt is equal to minus lambda n, where lambda is the decay constant. Not every radiogenic nuclide in the sample begins decaying at the same time. Therefore, lambda represents a cumulative decay constant for all atoms of the element in the sample. Lambda is a characteristic constant for radioactive isotope of any element. If N0 is taken as the number of radiogenic isotopes accommodated at the time of formation of the sample, N is the number of isotopes that are present today, one can obtain the relation between N0 and N by integrating the above equation. So integral minus dn upon dt is equal to integral lambda n. So one gets n is equal to n0 e to the power minus lambda t. Or one may also write n0 is equal to n into e lambda t, where e is the base of the natural logarithms, t is the time lapsed since the formation of the sample till present day. This is referred to as the decay rate equation. It is customary to mention the rate of decay of an isotope also in terms of the half-life of the isotope. Half-life is the decay time that will be taken by half the number of atoms of a radioactive isotope in any sample to reach the daughter element isotope. Since each parent nuclide produces only one daughter nuclide, the half-life is the time at which the number of daughter isotopes produced equals the number of parent isotopes remaining after the half-life. Mathematically, the half-life T by 2 is related to the rate of decay constant, that is, lambda by the expression T 1 by 2 is equal to 0.693 upon lambda. The half-lives of the decay mechanisms of isotopes like potassium-40, uranium-238, uranium-235, thorium-232, rubidium-87 and samarium-147 extend beyond 4 billion years. For example, the half-life of uranium-238 is about 4.5 billion years. That of thorium-232 is 14 billion years. And for samarium-147, it is 108 billion years. When deployed in conjunction with each other, these decay systems are found useful in determining the ages of the oldest lunar rocks, the age of oldest meteorites, and the oldest rocks on Earth. All point towards 4.5 to 4.6 billion years as the age of the solar system. In this episode, we have learned about the isotopes of elements and their stability, the generations of new elements beyond Fe56 by neutron capturing and by electron capturing, unstable and radiogenic nuclides beyond bismuth 209, emission of alpha-beta particles and the gamma rays during the radioactive decay, half-lives of radiogenic isotopes, decay constant lambda and its relation to half-life, the law of radiogenic decay, and also the decay rate equation. We will look again into the usefulness and the constraints of the different radiogenic isotope decay systems in the next episode.